A silent workshop holds a forgotten masterpiece of teamwork. We can uncover its secrets not by digging, but by doing. This is the world of experimental archaeology, a field that resurrects the ancient artisan team's entire workflow. By the end of this exploration, you will gain a completely new lens for viewing history, one that reveals the dynamic human collaboration behind every timeless object. How did a crew coordinate to drill through solid granite? What unspoken language kept a massive project moving? We will answer these questions by stepping into the reconstructed workshops of the past. What does true human collaboration look like when stripped of all modern technology? The very first step in this journey is to define the craft itself. This field, experimental archaeology, is not a hobby or a simple reenactment. It is a scientific discipline built on a powerful question. What if we could test our historical theories by physically rebuilding them? The process begins with a hypothesis, a researcher's best guess about how an ancient task was accomplished. They then move to the workshop, not the dig site, using only the tools and materials that would have been available at the time. The goal is not to create a perfect replica, but to encounter the same problems, the same physical constraints that an ancient artisan would have faced. This hands-on approach reveals something traditional analysis often misses. While archaeology expertly tells us what was left behind, experimental archaeology actively investigates how it got there. It fills in the silent gaps between artifacts with the sounds of labor, the feel of materials, and the logic of forgotten processes. This shift in perspective is profound. It moves our focus from the static object, alone in a display case, to the dynamic human system that created it. By engaging in the doing, we begin to see not just a tool, but the hand that held it. Not just a building, but the coordinated effort that raised it. This foundational method transforms anonymous history into a story of collective skill, setting the stage for us to meet the teams themselves. That golden mask in the museum case is a final, silent witness. For generations, history has been written by these witnesses, these singular, breathtaking objects that survived the centuries. But what if we have been asking them the wrong questions? We have at what they are, but rarely asked how they came to be. Experimental archaeology makes a fundamental, almost radical shift in perspective. It is not primarily interested in the product. It is obsessed with the process. The real historical artifact, it argues, is not the mask itself, but the invisible chain of events that forged it. This is the conceptual leap from object to workflow. Think of it like this. A detective arrives at a finished, beautifully set dinner table. By examining only the plates and silverware, they can describe the meal. But if they instead go into the kitchen, they find the true story. They see the chopped vegetables, the dirty pans stacked by the sink, the notes on the counter, the specific tools left out. This scene tells them not just what was eaten, but how many people were cooking, what their roles were, and the sequence of their actions. Experimental archaeology treats every ancient workshop like that kitchen. The researchers are the detectives, and their clues are the things often overlooked. They study the microscopic marks left by a specific chisel on stone, understanding the angle and force of the strike. They analyze piles of material waste, or to see where raw material was trimmed away and how efficiently it was used. They map the layout of a workshop floor, noting where tools were found relative to hearths or workbenches. Each of these clues is a piece of a larger blueprint. A scatter of flint flakes reveals the seating position of a toolmaker. The consistent angle of cut marks on 100 stone blocks points to a standardized technique taught across a team. From these silent testimonies, a picture of human collaboration begins to develop. The finished object, then, is merely a fossilized moment. It is the endpoint of a dynamic, living system of labor, communication, and shared knowledge. By reverse engineering that system, we stop seeing a statue. We start seeing the sculptor, the apprentice mixing plaster, the person hauling clay, and the overseer coordinating their movements. The artifact is no longer a solitary star. It becomes a single frame pulled from a much longer, richer film of collective human effort. And to understand that film, we need to identify the main characters. This deep material knowledge was the team's first and most vital asset. Before any design could be drawn or any tool lifted, the ancient artisans engaged in a profound conversation with the very earth itself. This is not merely about having resources, it is about possessing material intelligence. Experimental archaeology recreates this crucial first principle by insisting on absolute authenticity in sourcing. A team studying Bronze Age sword making does not order generic copper online. They locate the exact ore deposits used ago, often hiking to remote outcrops. They gather the specific type of charcoal that would have been made from local woods because the fuel's burning temperature is critical. In doing this, they immediately confront the logistical reality of the ancient team. Someone had to know where that special clay vein was hidden, the one that fired to a perfect red without cracking. Another member had to understand the seasonal growth of reeds for basket weaving, knowing which patch yielded the most flexible fibers. These procurers were not just laborers, they were the team's geologists, botanists, and quartermasters rolled into one. Their expertise formed the invisible foundation of everything that followed. By physically retracing these steps, researchers uncover a network of knowledge and trade. The choice of a particular granite quarry over another was not random. It was a calculated decision that balanced quality, travel distance, and the sheer effort of transport. This first decision, etched in stone and clay before work even began, dictated the rhythm, the tools, and even the size of the final creation. To walk that same path to the quarry is to understand the ancient team's opening move, a strategic commitment written not on parchment, but in the landscape itself. The true signature of a craftsman is not in their name, but in the wear pattern on their favorite hammer. This leads us to the second principle, the physical heartbeat of the workflow, tool replication and skill acquisition. An artisan is defined by their tools, and a team is defined by their shared toolkit. Here, experimental archaeology moves from theory to tangible, often frustrating reality. It is one thing to find a flint blade in the dirt. It is an entirely different challenge to make one. Researchers begin by sourcing the exact type of stone, learning to read its grain and flaws. Then comes the knapping, the precise art of striking one rock with another to shape a cutting edge. The first attempts are clumsy, producing useless shards and blunted stones. This initial failure is the entire point. It is a direct conversation with the past, a humbling admission that knowledge is not just intellectual, it is stored in the hands. Months of practice follow, developing the specific muscle memory, the exact angle of strike, and the intuitive feel for the material that every ancient toolmaker possessed. This process is repeated across disciplines, from casting bronze chisels in handmade clay molds to weaving sturdy baskets from gathered reeds. But making the tool is only half the story. The real revelation comes in learning to use it with proficiency. A researcher trying to carve a granite block with a replicated copper chisel quickly learns why certain designs prevailed. The soft metal blunts quickly, demanding a specific rocking motion to be effective. This hands-on struggle illuminates the invisible social structure of the ancient workshop. It reveals a clear hierarchy built on skill. The master craftsperson possessed a flawless, almost unconscious technique, born of a lifetime of repetition. The journeyman was still refining their craft, capable but requiring more focus and effort. The novice was relegated to simpler, preparatory tasks, learning the basics through observation and guided practice. Each was an essential cog in the production machine. The master might rough out the grand shape of a statue, the journeyman would refine the details of a garment, and the novice would be mixing plaster or maintaining the fire in the forge. This tiered system was not about inequality, but about efficiency and knowledge transfer. By spending years acquiring these lost skills, modern researchers do not just recreate objects, they resurrect the very ladder of learning that sustained ancient civilizations. They feel the progression from clumsy novice to competent craftsperson in their own bones, mapping the time and mentorship required to build a team. And once that team is assembled with their hard-won skills and trusted tools, they face their greatest test, a silent conversation with a material that does not wish to be shaped. Granite does not yield to a single strike, but to a relentless, intelligent sequence of blows. This brings us to the third, and perhaps most revealing principle, a French term meaning the operational sequence. Think of it as the ancient team's invisible instruction manual, the step-by-step roadmap that transformed a raw boulder into a polished monument. For experimental archaeologists, reconstructing this sequence is the ultimate logic puzzle. They must map every single action, from the moment material was sourced to the final touch on the completed object, and then test every possible order to find the one that makes sense. Take the creation of a simple stone axe. A researcher might start with a hypothesis. Perhaps the artisan first shaped the rough form, then attached a handle and finally sharpened the edge. But when they try this sequence, they encounter a problem. The final sharpening step is too dangerous, risking damage to the carefully fitted handle or the artisan's own hand. So they reverse the steps. They sharpen the blade first, while it is still easy to hold safely, then shape the body to fit the haft. This new sequence flows smoothly, minimizing risk and preserving the work already done. This is the power of the inaction. It is not about guessing the right answer. It is about systematically eliminating the wrong ones through hands-on trial. Every craft has its own critical sequence. In pottery, does the potter apply a decorative slip when the clay is wet, leather hard, or bone dry? Each choice produces a different visual effect and requires a different technique. By physically testing each option, researchers can look at an ancient pot and read its biography in the order of operations. They see the fingerprints left during initial shaping, the smoothing marks from a later stage, and the precise moment a handle was attached before firing. This reconstructed blueprint reveals more than technique. It exposes the team's collective intelligence. The most efficient sequence is almost always the one that conserves energy, reduces waste, and allows for specialization. One person could rough out 10 blanks, passing them to another who performs the fine finishing, while a third prepares the binding for handles. The workflow becomes an assembly line, conceived before the Industrial Revolution. By walking this path of actions, we stop seeing a static tool. We witness a dance of decisions, a flow of material and skill that turns chaos into creation. And to execute that dance perfectly, the team relied on a language far older than words. A symphony requires more than one type of instrument to achieve its full voice. This is the fourth principle, specialization and role division, where the abstract concept of a team crystallizes into specific, interdependent people. Experimental archaeology uncovers this social architecture through a simple, powerful method, the timed experiment. Researchers do not just make a tool, they clock the process. They measure how long it takes one person to perform every single task from start to finish. Then they break the work into segments and assign each to a different researcher, mimicking a specialized team. The results are often startling. One person attempting to both quarry a granite block and carve its intricate hieroglyphs would be an exercise in exhaustion and diminishing returns. The heavy, repetitive labor of quarrying would fatigue the muscles needed for the delicate, precise work of carving. The quality of the final detail would suffer, or the project would take an impractically long time. By splitting the work, efficiency soars. A strong individual with expertise in leverage and stone fracture can excel at the quarry, producing rough blanks at a steady pace. Those blanks are then passed to a carver whose hands are trained for subtlety, whose focus is undivided by the earlier brute force labor. This is not a modern insight, it is a rediscovery of ancient logic. Through these experiments, we can map a probable roster of specialists, the mastered geology and mass extraction. The rough-out carvers with heavy points and mallets gave the stone its basic shape. The fine detail artists, using a suite of finer chisels and drills, brought scenes to life. The polishers, with abrasives like sand and leather, achieved the final luminous finish. And overseeing it all, perhaps, was a master coordinator, an overseer who ensured the flow of material matched the pace of work, that the right blank reached the right hands at the right time. This reconstructed workshop is a mirror of society itself. It shows that great achievements were built on a foundation of recognized and respected expertise. The polisher did not yearn to be the carver, their pride was in achieving a perfect, reflective surface. This interdependence was the engine of productivity. It allowed for the parallel processing of tasks, minimized downtime, and created a system where the collective skill was far greater than the sum of its individual parts. We stop imagining a faceless crowd of laborers and begin to see a community of experts, each person's identity woven into the social fabric of their craft. And for this community to function, they needed to communicate in a language that flowed as smoothly as the materials they shaped. The rhythm of a workshop is a kind of music, composed not of notes, but of synchronized actions. This brings us to the fifth principle, the silent symphony of communication and verbal cues. In the din of a bronze foundry or across the sun-baked expanse of a temple construction site, shouted conversations were impractical and wasted precious energy. How did a team of 20 individuals move a ton stone block in perfect unison, or know precisely when to pour molten metal into a mold? Experimental archaeology investigates this by putting researchers into the very situations where communication would break down. They do not just make tools, they use them together on a shared task, under the authentic conditions of noise, distance, and physical strain. The discoveries are profound. They find that the work itself generates its own essential language. A specific, measured tap of a wooden mallet on a stone block is not just a strike, it is a command. It tells the team on the other side of the stone to insert their levers. 2 rapid taps might mean to stop, to hold position. A foreman overseeing a brick-laying crew did not need to shout over the constant slap of mortar. A simple, raised hand could direct the next brick to the left. A pointed finger could indicate a correction in alignment. By attempting to build a wall or raise a post using only the tools and plausible signals of the era, researchers experienced the birth of this operational shorthand. It is a language of absolute necessity and stunning efficiency. Each signal is refined through repetition and shared failure, until it becomes instinct. This cultivated rhythm transforms a group of individuals into a single, cohesive organism. The carver learns the sound of the quarryman's hammer, knowing the next rough block will be ready soon. The apprentice feels the subtle shift in the master's posture that means they should bring a finer chisel. This unspoken understanding is the glue of the workflow. It minimizes hesitation, prevents accidents, and creates a fluid pace where everyone is anticipating the next move. To reconstruct this communication is to witness the human mind solving a fundamental problem of collaboration. It reveals that the greatest projects of antiquity were not accomplished in a chaotic roar, but in a focused, almost meditative silence, punctuated by the purposeful sounds of work. Every tap, every glance, every coordinated heave was a word in a forgotten dialogue, one that literally moved mountains. And once this dialogue perfected the process, it had to face the ultimate test of reality, where theory meets the unyielding constraints of the physical world. The most efficient workshop is a living map of human movement. This brings us to the 6th principle, workspace dynamics and layout. The architecture of work, it turns out, shapes the work itself. Experimental archaeologists do not just replicate tools or techniques, they physically reconstruct the entire stage where the ancient drama of creation unfolded. This means building the workshop floor as it was found, using only the lighting from replica oil lamps or the sun through a theoretical window, and arranging tools in the exact scatter patterns discovered by excavators. They then step into this space and try to work. The goal is simple, to feel the logic of the layout in their own muscles. Was the potter's wheel placed conveniently near the clay storage, or did the artisan have to take 10 unnecessary steps with a heavy, wet lump each time? By physically performing the tasks, the optimal layout emerges from experience, not just theory. A fascinating example comes from studies of flint knapping sites. Archaeologists might find a dense concentration of stone flakes in one area, with finished tools found a few feet away. By recreating this scatter pattern in a sandbox and then knapping stone themselves, researchers can literally sit in the ancient artisan's seat. They discover that the debris pile marks the primary work zone, where the rough, dangerous flakes fly. The clear area nearby is where the finer, finishing work happened, safe from sharp debris underfoot. This is not a random mess, it is a preserved blueprint for safety and efficiency. The workshop layout becomes a silent project manager. Positioning a stone carving station to catch the morning sun provided hours of perfect, shadow-reducing light for detailed work. Storing heavy bronze ingots near the furnace, rather than across the room, conserved immense physical effort over the course of a day. Even the placement of a water jar or a grindstone for sharpening tools reveals a profound understanding of ergonomics. Every saved step, every minimized reach, across a team and across years, translated into monumental gains in productivity. The space itself was engineered to foster a collaborative flow. A central shared workbench might allow a master to demonstrate a technique to several apprentices at once. A specific tool rack, always in the same place, meant any team member could fetch a chisel without interrupting another's concentration. By rebuilding and inhabiting these spaces, researchers do more than understand ancient engineering, they feel the rhythm of a day in the life of the team. The workshop transforms from an empty floor plan into a dynamic instrument, perfectly tuned to the symphony of skilled hands. And just as a musician must tune their instrument, the ancient team had to constantly listen to the feedback from their most critical partner, the stubborn, unpredictable materials they sought to master. A monument does not just occupy space, it consumes time. This leads us to the seventh and perhaps most humbling principle: time and labor estimation. Here, experimental archaeology moves from recreating how something was done to quantifying the staggering human effort it required. By meticulously timing each step of the reconstructed operational sequence with teams of varying skill, researchers can build a realistic model of the past's true cost, measured not in gold, but in lifetimes of labor. Imagine a researcher, their hands aching from a day of shaping just one limestone block with copper tools. They have a precise log, a modern spreadsheet filled with ancient effort. It took 3 hours to quarry the rough shape, 2 more to transport it 100 yards on a wooden sledge, and 6 grueling hours of pounding and grinding to achieve a flat surface. That is 11 hours for a single, unfinished block, performed by a skilled practitioner. Now, multiply that by the 10,000 blocks in a small pyramid's core. Suddenly, the abstract scale of the monument collapses into a tangible, breathable reality of sunburned backs, worn hands, and years of sustained, coordinated exertion. This methodology transforms our understanding of historical scale from a spectator's awe to a project manager's sober assessment. How many person-hours did it take to weave the intricate threads of a royal tapestry on a hand loom? How many teams, working in shifts, were required to maintain the constant heat of a bronze foundry for a week-long casting? These are no longer unanswerable questions. By timing the weaving of a single square inch with period-accurate techniques, then scaling up, researchers can estimate the months of focused labor behind a textile masterpiece. They reveal that such objects were not merely decorations, but literal investments of human life, calendars made manifest in wool and dye. These time studies force a profound shift in perspective. We are compelled to see the Great Wall not as a static line on a map, but as a centuries-long logistical campaign, a slow, relentless tide of labor advancing across the hills. A cathedral becomes less a symbol of faith alone and more a triumph of generational project management, where the master architect's vision had to be translated into daily quotas of stone, mortar, and skilled wages. The monument itself becomes a clock, its size and complexity a direct measure of a society's ability to organize, feed, and motivate its people across decades. This quantification does not diminish the artistry, it elevates the collective human achievement to something even more extraordinary. Granite yields its secrets only to a perfectly sustained rhythm. This brings our principles into sharp focus with a tangible puzzle from the sands of Egypt. Scattered around ancient workshops, archaeologists have long found stone vessels of breathtaking precision, carved from materials like granite and basalt, some of the hardest stones on Earth. The surfaces are smooth, the walls are evenly thin, and the hollowed interiors are perfectly cylindrical. For decades, the question haunted historians. How could a civilization without hardened steel or powered tools achieve such flawless work? The answer, revealed through experimental archaeology, lies not in a magical lost technology, but in the elegant choreography of a small, dedicated team. Researchers began by dismissing complex theories. They looked at the evidence left behind, the unfinished vessels abandoned in workshops, the simple copper tubes and rods found nearby, and the ever-present sand of the desert itself. Their hypothesis was beautifully simple. Perhaps the Egyptians used a basic bow drill, but with a critical gritty partner, sand. They replicated the likely tools, a copper tube fixed to a wooden shaft, a bow with a leather strap, and a pile of ordinary quartz sand. Then they assembled their modern team to test the ancient workflow. One person knelt, placing the copper tube tip onto a marked spot on a granite block, applying firm, consistent downward pressure. A second person took the bow, looping its strap around the drill shaft, and began a steady, rhythmic sawing motion back and forth. This action spun the copper tube, grinding its edge against the stone. But copper alone is softer than granite. Here is where the third team member played their part. Another person would periodically sprinkle wet sand into the growing hole. The quartz grains in the sand, harder than the copper but not as hard as the granite, became the true cutting agents. They embedded themselves in the copper's edge, turning the soft metal tube into millions of tiny, sharp teeth. As the drill spun, these quartz teeth slowly, relentlessly, powdered the granite beneath them. The experiment was a revelation in human coordination. The person applying downward pressure had to be unwavering. Any tilt would create an uneven, bell-shaped hole. The person working the bow had to maintain a perfectly consistent rhythm, a slow and steady pace that kept the sand grinding effectively without overheating or jamming. The assistant managing the sand and water had to time their interventions perfectly. Too much would clog the drill, too little would halt progress. This was not a job for a solitary genius. It was a symphony in 3 parts. The sustained effort required was immense. Drilling just 1 inch into solid granite could take hours of this unbroken, synchronized labor. But that very difficulty explains the mastery. This workflow, born of necessity, could only be perfected through generations of practice. A master driller would develop an instinct for the right pressure. A bow worker would learn the song of the perfect rhythm from a lifetime of listening to the drill's grind. The apprentice started by wetting sand, learning the pace and the team's verbal cues before ever touching the bow. The stone vessel, therefore, is not just a container. It is a fossilized recording of that rhythm. Its perfect symmetry is proof of a team's shared focus, its thin walls a testament to their collective patience. What seemed like an impossible task becomes, through experimental recreation, a profound lesson in human collaboration. The mystery of the granite vessel is solved not by finding a better tool, but by understanding the better team. The rhythm of the Egyptian drill team solved one mystery of precision, but an empire was built on a different kind of rhythm altogether, the relentless beat of mass production. High above the bustling streets of Rome, on the rooftops of countless buildings, lay the evidence of this industrial genius, the humble fired clay tile. These were not unique artworks, but thousands of identical interlocking pieces, each one a testament to a system of collaboration so effective it clothed an empire in a skin of. Experimental archaeology has turned its focus to these unassuming objects, reconstructing entire Roman tile factories to uncover the workflow of the ancient world's first true manufacturing lines. To understand this system, we must start not with the tile, but with the earth beneath it. Researchers begin by sourcing the correct clay, often from pits near known Roman sites. The first team encountered is not the master craftsmen, but the laborers, the individuals who dig, transport, and clean the raw material. This initial, brutish work is critical, for any stones or organic matter left in the clay will cause a tile to crack or explode in the kiln. By processing the clay themselves, using only water and sieving techniques from the era, the modern team immediately feels the physical demand of this foundational role. It is a reminder that every industrial process rests on the shoulders of those who prepare the stage. Once the clay reaches the perfect plastic consistency, it moves to the heart of the factory, the molding station. Here, the principle of specialization comes alive. Experiments show that using standardized wooden formers, essentially reusable molds, is the only way to achieve the uniformity the Romans demanded. A specialist, sometimes called a, would have performed this task with a speed born of repetition. They would take a measured lump of clay, slam it into the mold with a practiced thud, scrape off the excess with a wire or wooden strike, and then deftly flip the former to release a perfect, wet blank. This action, repeated hundreds of times a day, was not mindless. It required an intimate knowledge of the clay's behavior, knowing exactly how wet it needed to be to release cleanly without losing its shape. The efficiency here is staggering. While one person might hand sculpt a single tile in an hour, a skilled molder with a good team supporting them could produce dozens in the same time. The wet tiles then enter a delicate phase, the drying process. This is where workspace dynamics prove their importance. Experimental reconstructions show the tiles were laid out in long, organized rows on raised wooden racks or clean floors. This layout was not an accident. It allowed air to circulate evenly around each tile, preventing warping, and it created a logical flow. An apprentice could easily move down the rows, checking for cracks, while the organized spacing prevented accidental collisions that would ruin hours of work. The drying yard was a physical calendar, with tiles at one end just placed and tiles at the other end ready for the kiln, providing a constant visual inventory of production. Finally, the tiles faced their trial by fire. The Roman kiln was a massive brick-lined dome, a collaborative project in itself to build. Firing it was the ultimate team exercise, a multi-day ballet of heat management. One team was responsible for steadily feeding the firebox with the correct fuel, maintaining a precise and gradual temperature increase over many hours. Another team, perhaps more experienced, monitored the kiln's color and the tiles visible through spy holes, using their hard-won knowledge to judge when the peak temperature was reached and when to begin the slow, controlled. A single mistake by either team, a rush of heat or a draft of cold air, could shatter an entire batch, wasting weeks of collective labor. This shared risk baked quality control directly into the social structure. Different teams would be responsible for different batches, their work literally stamped with a maker's mark. This was not just about pride, it was about accountability, a system that linked a team's reputation directly to the physical integrity of the tiles they produced. What emerges from the smoke of the experimental kiln is a clear picture of Roman industrial thinking. Every step from the clay pit to the loading of a shipment barge was designed for scale and transport. The standardized size and shape meant tiles could be stacked neatly, packed tightly into ships and carts, and assembled quickly by builders anywhere in the empire from Britannia to Syria. The tile itself is a modular component of a much larger system. By recreating this workflow, we see the Roman genius not in a singular invention, but in their mastery of the collaborative chain. They understood how to break down a complex task into simple, repeatable actions, distribute those actions to specialized teams, and synchronize the entire process to achieve a goal far beyond the capability of any individual artisan. The rooftops of Rome, therefore, are more than just shelter. They are a mosaic of forgotten teams, a testament to the power of a system where every person, from the clay digger to the kiln master, was an essential cog in an empire-building machine. A ship is not built in a forest, but the forest is the first member of the crew. For the Vikings, the quest for a new longship began with a silent, careful search through the oak groves. Experimental archaeologists recreating this process quickly learned that not every tree will do. The master shipwright, the central figure in this entire enterprise, was first and foremost a master reader of wood. He walked among the towering oaks, looking for a trunk with the perfect natural curve, a gentle sweep that could become the soaring keel or the elegant stem of the ship. This was not carpentry, it was a form of prophecy, seeing the finished vessel hidden within the living grain. Once the chosen trees were felled, the true collaboration began, and it started with a thunderous crack. Using heavy iron wedges and enormous wooden mallets, a team would split the great logs along their natural radial lines, following the wood's own internal logic. This technique, called riving, was fundamental. It produced planks that were far stronger than any sawn timber, because the wood's fibers remained unbroken, running the full length of the piece. The sound of the splitting oak was the first beat of the ship's heart, a declaration that the project was. Each massive plank, now rough and dripping with sap, was then passed to another specialist. Using a broadaxe with a breathtakingly sharp, curved blade, these craftsmen would skillfully hew the wood into its final, tapered shape. Watching a modern practitioner master this skill reveals its incredible danger and precision. A single misplaced swing could ruin weeks of growth and labor, turning a precious plank into firewood. The hewer had to understand the wood's personality, its knots and twists, and work with them. This phase of the work was loud, physical, and profoundly communal, a symphony of iron on oak that shaped the very bones of the ship. And as these bones were prepared, another essential team was at work, their craft glowing with heat. The ship could not be held together by nails alone. It required thousands of iron rivets, each one forged by hand. The ironworker and their assistant were the providers of the ship's sinew. They would heat iron rods in a charcoal furnace, hammering one end into a flat rove and leaving the other to be pointed. The rhythm of their small forge provided a constant, metallic counterpoint to the deeper thud of the axes. Their output dictated the pace of assembly, a reminder that every specialist was linked in a delicate chain of supply. With the planks shaped and the rivets piled high, the most iconic stage of construction could begin, the clinker-built assembly. This is where the Viking workflow reveals its genius for turning complexity into a repeatable, teachable process. The keel was laid down first, the backbone of the ship. Then, the shipwright and their team began attaching the planks, starting from the bottom. They would overlap the lower edge of a new plank over the upper edge of the one below, drilling holes through both layers at precise intervals. A rivet was inserted from the outside, a washer called a rove was placed on the inside, and the pointed end of the rivet was hammered over to clamp the two planks together with immense, permanent force. This created the Longship's distinctive stepped hull. But here was the hidden challenge, one that experimental rebuilds make painfully clear. Each plank was not a flat board. It was a subtly twisted, three-dimensional sculpture, tapering in width and thickness from one end to the other. As the hull rose, each new plank had to bend in multiple directions at once, flaring outwards to create the hull's shape. This is where the team's adaptive problem-solving came into play. They used fire and water to steam bend the toughest sections, a technique requiring careful coordination to avoid scorching the precious wood. They employed ropes and wooden clamps to hold planks in position while riveting, a task needing many hands. The master shipwright, with their design held not on parchment but in their mind's eye, would move constantly around the growing shell, sighting down curves, calling for adjustments, ensuring that the emerging form matched the vision born months earlier in the forest. Finally, with the hull complete, the last specialists moved in, the caulkers. Their job was to make the vessel watertight. They would take strands of animal hair, often from sheep, and dip them in sticky heated pine tar. This fibrous tarry rope was then carefully hammered into the seams between the overlapping planks with a mallet and a blunt iron wedge. The smell of hot pine tar and the soft thumping of the caulking irons signaled the final act of sealing the team's work from the sea. What experimental archaeology uncovers in this entire process is more than a shipbuilding manual. It reveals a social organism. The master shipwright was the architect and conductor. The inhewers were the primary muscle, the ironworkers the vital suppliers, and the caulkers the finishers. Each relied on the other's flawless execution. A poorly rived plank would not bend true. A weak rivet would fail in a North Atlantic storm. The workflow was a cascade of trust and skill, where every person's labor was literally riveted to their neighbors. The finished Longship, therefore, was never just a vehicle. It was the physical manifestation of a community's shared knowledge, a symphony of coordinated action frozen in oak and iron, ready to carry its builders across the known world. A master's knowledge was their most guarded treasure, yet it had to be spent to survive. Beyond the immediate rhythm of production, every ancient workshop faced a deeper challenge, the silent clock of human mortality. How did a complex craft, refined over a lifetime, not vanish when its master passed on? Experimental archaeology turns its attention to this vital human element, the slow, careful dance of apprenticeship and knowledge transfer. Here, researchers do not just replicate objects, they replicate the learning process itself, stepping into the roles of teacher and student to map the invisible curriculum of the past. This investigation begins with a simple, humbling experiment, the broken pot. A modern researcher, attempting to throw a vessel on a replica kickwheel for the first time, quickly creates a wobbly, collapsed mess. The clay refuses to center, the walls buckle under uneven pressure, and the piece is only good for the recycling bin. This first failure is a direct portal into the ancient novice's world. How many such failures were considered an acceptable cost of education? By deliberately tracking their own progress, researchers can estimate the sheer volume of raw material and time invested in creating a single competent potter. It might take months of daily practice before a novice's hands internalize the precise touch needed to raise a thin, even wall. This tangible learning curve reveals a critical economic truth. Apprenticeship was a significant investment for the master and the community. The broken pots, the wasted bronze, the misshapen stone blocks, these were the tuition fees of the ancient world, paid in material and patience. This framework helps us see where beginners were carefully inserted into the workflow. They were not thrown into the most difficult or dangerous tasks. Instead, masters strategically placed them in roles where failure was less costly and learning was organic. A novice in a flint knapping workshop might start by simply gathering the right type of stone, learning to identify quality material by sight and feel. In a weaving collective, a young apprentice would begin at the loom's edge, perhaps just beating down the weft thread with a comb, feeling the rhythm of the work before ever touching the shuttle. In a metalworking team, a newcomer would be tasked with maintaining the charcoal fire, a job that taught the critical relationship between air, fuel, and temperature through constant, hands-on monitoring. These were not mere chores, they were the first chapters of a living textbook. Through this guided participation, the novice absorbed the culture of the workshop, its unspoken rules, its rhythms, and its shared language of gestures and sounds. The master, in turn, gained an extra pair of hands for preparatory work, and the profound satisfaction of seeing their craft endure. This relationship formed the social contract at the heart of ancient industry. The master provided food, shelter, and priceless knowledge. The apprentice offered their labor and a solemn promise to uphold the craft's standards. This system ensured that proprietary techniques, the special glaze recipe, or the secret method for tempering steel, did not disappear. They were passed along a human chain, from one generation to the next, each link strengthening the workflow against the erosion of time. The survival of a complex technology for centuries, like the lost wax method of bronze casting, is not a historical accident. It is the direct result of this deliberate, intimate transfer of embodied skill. When we look at a perfectly symmetrical Greek vase or a flawlessly balanced Roman sword, we are therefore seeing more than an object. We are witnessing the final exam of a long graduated apprentice, the culmination of countless patient lessons, gentle corrections, and broken prototypes. The artifact stands as a testament not to one master, but to an unbroken lineage of masters and students, a conversation in clay and metal that spanned generations. A perfect bronze cast hides its story, but a failed one tells it aloud. This is the counterintuitive heart of experimental archaeology, where a shattered mold or a fractured stone is not a setback, but a breakthrough. In a modern laboratory, such an outcome would be discarded, assigned to recalibrate the machine. In the reconstructed workshop, it is a direct message from the past, a clear signal pointing to the exact moment where ancient knowledge made the difference between triumph and ruin. These deliberate recreations embrace failure as the most honest form of data. When researchers attempt to move a 2-ton block on a wooden sledge and it grinds to a halt, they are not just experiencing a problem, they are isolating a variable. Perhaps the path needed more water or mud as a lubricant, a detail only mentioned in passing in some texts. The failure proves its necessity. When a team tries to cast a bronze sword using a slightly incorrect alloy mix or a poorly vented clay mold, the metal might not flow completely, leaving a blunted, useless form. This miscast is a fossilized mistake. It shows the narrow window of success the original metalworkers operated within. Their expertise was not just in doing the task, but in knowing the 100 subtle ways it could go wrong and how to prevent each one. These experiments measure the ancient margin for error, which was often vanishingly small. They highlight the negotiable skills, the ingrained instincts that separated a master from an apprentice. A novice might not notice the faint, wrong smell of the kiln, indicating a dangerous temperature spike. A journeyman might misjudge the curing time for a clay core, leading it to explode during a pour. Each replicated failure maps a point of critical knowledge in the operational chain. But beyond prevention, these mistakes reveal something even more profound: the adaptive intelligence of the ancient team. A stone that fractures during shaping is not simply thrown away. The experimental team, just like their ancient counterparts, must now troubleshoot. Can the stone be salvaged for a smaller object? Can the fracture line be incorporated into the design? This on-the-fly problem-solving, born from material reality, showcases the dynamic flexibility within seemingly rigid traditions. The workflow was not a robotic script. It was a living dialogue with the physical world, and the teams were fluent in its language. Every crack and bubble preserved in the archaeological record becomes a lesson plan, a silent instruction left behind by those who learned the hard way. By courageously failing in the same manner, modern researchers don't just learn how things were made, they begin to think like the makers, navigating the same narrow path between possibility and disaster that defined the ancient craft. The shattered casting or the fractured stone tells one story, but the human eye can only see so much. To truly listen to these ancient materials, experimental archaeology has formed a powerful partnership with the modern laboratory. Here, technology does not replace the hands-on work, it becomes its most attentive witness. The goal remains pure, to use only the tools of the past, but researchers now employ a suite of silent observers to capture every detail of the resurrected workflow. Three-dimensional scanning is often the first step. Before a single experimental stone is knapped or a pot is thrown, a pristine artifact is scanned to create a perfect digital twin. This model becomes the ultimate benchmark. Later, when the experimental replica is complete, it too is scanned. The software can then compare the two with impossible precision, measuring the subtlest differences in curvature, wall thickness, or tool mark depth. This tells the researcher not just if they got it close, but exactly where their technique diverged from the ancient masters, guiding their next attempt with data rather than guesswork. The microscope becomes another window into the past. When a researcher uses a replicated flint blade to cut rope or scrape hide, they then place that blade under high magnification. They are looking for the tiny polishes, scratches, and fractures that form on the tool's edge. By comparing these patterns to those found on genuine artifacts, they can confirm the tool's exact use. Was this stone point a hunting weapon, a woodworking tool, or a ceremonial object? The microscopic story written on its edge provides the answer, validating or correcting the experimental hypothesis. Perhaps the most revealing modern witness is the high-speed camera. The act of, for instance, happens in a blur. The hammerstone strikes the core, and a flake flies off in milliseconds. To the naked eye, it is a single event. But with slow-motion video, every microsecond is laid bare. Researchers can analyze the exact angle of the strike, the point of impact, and the follow-through. They can see how a minuscule twist of the wrist changes the flake's trajectory, or how the core must be supported to prevent a catastrophic break. This transforms an intuitive skill into a teachable sequence of physics, allowing the technique to be broken down, understood, and refined. Beyond observation, chemical analysis deciphers the invisible ingredients of the past. A strange residue in the bottom of a clay pot or a glossy substance on a stone tool can be tested using methods like gas chromatography. This might reveal traces of ancient beeswax, pine resin, or animal fat. An experimental archaeologist can then attempt to replicate that exact adhesive, testing its holding power and working properties. When their replica adhesive leaves a chemical signature that matches the ancient sample, it is a powerful confirmation. It proves not just that something could be done, but that it very likely was done in that specific way. This marriage of old and new brings profound validation. The embodied experience of the researcher, the aching muscles and intuitive breakthroughs, is essential, but the data from scanners and microscopes provides an objective check. It prevents the story from becoming just a compelling narrative, anchoring it in measurable, repeatable facts. The technology allows researchers to quantify concepts like efficiency and force. They can calculate how many calories of energy a certain quarrying technique consumes, or measure the exact pounds of pressure needed to drive a copper saw through limestone with an abrasive sand. This turns abstract notions of ancient labor into concrete numbers, building a robust, scientifically grounded understanding of the past's physical reality. The workshop of the experimental archaeologist is therefore a unique bridge in time, where the feel of flint in the hand is illuminated by the cold, clarifying light of a digital scan. The workshop is a world in miniature, but history's greatest puzzles were built on a continental scale. To understand the pyramid or the cathedral, we must zoom out until the single artisan vanishes from view, replaced by rivers of stone and tides of human movement. Here, experimental archaeology faces its ultimate test, moving from the intimacy of the craftsperson's bench to the breathtaking complexity of the macro workflow. This is the realm of logistics, the silent symphony of supply and coordination that turned impossible dreams into permanent landscapes. Researchers approach these monumental projects not by attempting the impossible, but by isolating their most puzzling components and testing them in the real world. The central, haunting question is always one of motion. How do you persuade a mountain to walk? The answer lies not in magic, but in orchestrated repetition. Teams have reconstructed ancient Egyptian sledges from archaeological depictions, loaded them with concrete blocks matching the weight of real pyramid stones, and attempted to pull them across desert sands. The immediate discovery is visceral, the friction is immense. The sledge digs in, refusing to budge for a team of 20 strong individuals. Then, a crew member pours water on the sand ahead of the runners. The physics transform instantly. The dampened sand grains bind together, creating a firm, slick surface. The sledge now glides forward with a fraction of the effort, a simple solution hiding in plain sight within tomb paintings showing water bearers alongside hauling teams. This single experiment illuminates a cascade of logistics. It means the project required not just pullers, but a dedicated water transport team working in perfect sync ahead of the stone. It dictates the path, which must be inaccessible to water carriers. This one action, pulling a block 100 yards, reveals the interconnectedness of roles, The quarry team, the road preparation crew, the haulers, and the water bearers, all moving in a staggered, continuous rhythm like gears in a vast machine. But moving the stone is only the first act. The true logistical nightmare is sequence and placement. How do you ensure the right block, out of thousands, arrives at the right ramp at the right moment, in the correct orientation? Experimental projects modeling cathedral construction use scaled-down blocks and crane replicas to test medieval lifting techniques. They find that the workflow demanded a kind of living architecture, a dynamic blueprint where the construction schedule dictated the quarrying schedule. The stones for the foundation were not only the largest, they were the first to be cut months or years in advance. As walls rose, the required blocks became smaller and more specialized, the arched window lintels, the delicate pinnacle stones. This meant the quarry was not a chaotic hole in the ground, it was a carefully managed outdoor factory, with teams extracting different stone types in a precise order that matched the building's growth far away. The master mason's mind had to hold two timelines simultaneously, the slow ascent of the walls and the slow emergence of stones from the earth, synchronizing them across miles of countryside. This macro coordination extended to the most human of needs, sustenance. A workforce of thousands cannot build on an empty stomach. Logistics simulations estimate the staggering daily caloric intake required, translating it into tons of grain, fish, and beer. Experimental archaeology contributes here by recreating ancient baking facilities at workers' villages near monument sites. By determining how many loaves a single oven could produce per day, researchers can extrapolate the number of bakeries, and thus the size of the support economy, needed to keep the project fed. The pyramid rises not just from stone, but from a mountain of bread. Every baked loaf represents a farmer, a miller, a brewer, and a porter, an entire shadow economy dedicated to fueling the primary task. These scaled-down experiments and simulations paint a new picture of ancient ambition. They show that the true wonder of the Great Pyramid is not its height, but its inventory management. The miracle of Chartres Cathedral is not its spire, but its supply chain. These were enterprises that transformed entire regions into single, purpose-driven organisms. The quarry team, the transport crew, the lifting engineers, the carvers on site, and the army of supporters feeding them all were not separate groups. They were interdependent components of a single workflow stretched across time and space, a collaboration so vast it reshaped the land itself, leaving behind not just a monument, but a permanent lesson in what humanity can achieve when it organizes toward a single staggering goal. Stone dust hangs in the air, a dry taste on the tongue with every breath. This was the true atmosphere of creation, a world of overwhelming sensation that pure artifact analysis can never capture. To step into a reconstructed workshop is to be engulfed by its soundscape. The defining noise is not a single sound, but a layered chorus. Underneath everything is the low, rhythmic thud of heavy mallets driving stone wedges into timber, a deep heartbeat felt in the chest. Over this, a sharper, faster percussion, the relentless tap-tap-tap of a bronze chisel being driven into granite by a lighter hammer, a sound like impatient rainfall on stone. In a squatter, this rhythm gives way to a constant, roaring hiss from the bellows feeding a charcoal furnace, punctuated by the bright, ringing clang of hammer on anvil as a glowing billet of iron is shaped. These sounds were not just noise, they were vital communication. A master craftsperson could diagnose the quality of a strike, the health of a furnace, or the progress of a cut simply by listening. A change in the pitch of the chisel's ring might signal it was going blunt. A faltering in the bellows hiss meant the fire was dropping to a dangerous temperature. The workshop was alive with this auditory feedback loop, a language of labor that every team member understood intuitively. Then there are the smells, equally defining and inescapable. The acrid, eye-watering scent of burning charcoal permeates everything, clinging to hair and clothing. In a bronze foundry, this mixes with the sharp, metallic tang of heated copper and tin, and the earthy smell of burning clay from the molds. A tannery workshop carries the pungent, organic odor of hides and the distinctive smell of oak bark used in the curing vats. These aromas were not merely background, they were constant indicators of process. A master potter knew their kiln was at the perfect temperature partly by the specific smell of the clay and glaze vitrifying. A resin worker could tell when a batch of pine pitch was ready by its fragrance. This sensory immersion did something profound to the human mind. Researchers working for hours in these replicated environments often report a shift in their own consciousness. The constant, repetitive sound of their own labor, the rhythmic scraping of a hand adze or the steady pull of a bow drill, combined with the focused visual task, can induce a state of deep, almost trance-like focus. This phenomenon, sometimes called being in the zone, would have been a daily reality for the ancient artisan. It was a mental state that allowed for hours of sustained, precise work without mental fatigue, a natural consequence of the sensory environment they built. This shared sensory experience also forged powerful group cohesion. A team pulling a heavy sledge together falls into a shared breathing rhythm, their footfalls and grunts of effort creating a unified pulse. The synchronized clang of multiple hammers on a single bronze casting creates a driving, musical cadence that aligns the workers' movements. To be surrounded by the same sounds, smells, and tactile sensations day after day built a profound, unspoken bond. It created a collective sensory memory that defined the team's identity as much as their shared skills did. The finished artifact, resting silent and clean in a museum, has been stripped of this vital context. It carries none of the ringing clamor of its birth, the smell of the forge that birthed it, or the gritty feel of the dust that coated its makers. Experimental archaeology does more than rebuild tools and techniques. It resurrects this lost sensory world. It reminds us that history was not a silent film, but a vibrant, noisy, and aromatic symphony of human effort, and that the rhythm of work was the melody that held the entire team together. The chisel strikes the stone in a rhythm older than any blueprint. Yet behind every physical action lay an invisible framework of belief and tradition. Workflows in the ancient world were never purely mechanical equations of force and material. They were deeply woven with cultural constraints and ritual significance, a layer of meaning that experimental archaeology must strive to hear, not just see. When researchers meticulously recreate a technical process and still hit a baffling wall, the answer often lies not in physics but in philosophy. They might find a step in a ceramic firing sequence that seems to waste precious heat, or a tool sharpening method that appears unnecessarily complex. From a modern, efficiency-obsessed viewpoint, these are puzzling inefficiencies, but through the lens of cultural context, they transform into essential acts. These were the silent protocols that turned labor into ceremony and a workshop into a sacred space. To understand this, experimental teams must look beyond the toolshed. They integrate ethnographic studies of living craft traditions and pore over historical texts, searching for the spiritual architecture that surrounded the work. Consider the lighting of a bronze casting furnace. The technical steps are clear: prepare the charcoal, build the fire, pump the bellows. But what if a historical account mentions that the master metalworker always offered a handful of grain to the fire first, or recited a specific invocation to the god of the forge? This is not a decorative flourish. By incorporating this ritual into their experimental recreation, researchers begin to feel its function. That moment of focused silence before the roaring heat serves as a mental transition. It marks the shift from preparation to the point of no return, gathering the team's collective concentration and acknowledging the shared risk of the dangerous pour ahead. It provided a psychological anchor, a ritual of readiness that managed the very human anxiety surrounding a procedure where a single mistake could waste months of work. These practices structured the entire workday, carving the relentless flow of labor into meaningful chapters. A specific song sung while grinding grain on a quern stone transformed a monotonous, physically taxing job into a measured, rhythmic activity. The song's length might even correspond to a standard amount of grain processed, a melodic timer. The act of always passing a chisel with the left hand or entering a weaving lodge from a certain direction reinforced a sense of order and belonging. These were the unwritten rules that every apprentice learned not through lecture, but through immersion. They created a predictable, respectful environment, a psychological safety net within the demanding physical world of the craft. To break a ritual was not just a breach of protocol, it could be seen as inviting misfortune, disrupting the harmony necessary for success. This ritual layer ultimately fortified the team's shared identity. They were not just individuals who could shape clay, they were the people who knew the correct prayers for the kiln, the proper way to honor the spirit of the tree that became their loom. Their common knowledge created a powerful in-group bond, setting them apart from the rest of society. The workflow became a lived tradition, a story they acted out together with every project they completed. The finished object, therefore, carried this layered biography. It was born from technical skill, yes, but it was also midwifed by ceremony and collective belief. The vessel was not just fired, it was blessed. The sword was not just quenched, it was consecrated. By attempting to walk in these ritual footsteps, modern researchers gain a humbling insight. They see that for the ancient artisan, efficiency was not merely a matter of speed or material conservation. True efficiency resided in a process that was technically sound, socially cohesive, and spiritually complete, a harmony that resonated through the entire community. A bronze sword's true price was not measured in gold, but in the months of a master's life. This is the profound economic insight that emerges from the workshop floor, where the reconstructed workflow transforms from a story of skill into a ledger of ancient value. By meticulously logging every hour spent quarrying ore, smelting copper and tin, crafting the clay mold, and executing the perilous pour, researchers can assign a startlingly concrete cost to objects we usually view only as art. They move beyond admiring a sword's elegant curve to calculating its birth in calories consumed, tools worn down, and the collective focus of a specialized team diverted from all other tasks. This quantitative lens reveals the artifact as a dense packet of frozen labor, a physical manifestation of an ancient economy's most precious resource, human time. So how do we begin to set an exchange rate for the past? The process starts with the most fundamental unit, the daily subsistence of the artisan. Experimental projects estimate the caloric intake needed for such demanding physical work, often translating it into staple foods like grain. If a potter and their apprentice working together could produce 5 storage jars in a week, and their weekly food requirement was 1 bushel of grain, then those 5 jars effectively cost 1 bushel to produce. This creates a baseline, a primitive but powerful price tag. Suddenly, trade patterns make new sense. A community living in rocky highlands with poor clay might gladly exchange several bushels of grain for a single sturdy jar from a lowland pottery workshop, because the alternative would be spending far more of their own labor and food to travel and learn the craft themselves. The jar is not just a container, it is a stored offering of another community's specialized time and energy. This logic scales to the most luxurious items. Take that exquisitely carved jade pendant from an ancient tomb. Experimental work shows that drilling and polishing jade with simple stone tools and abrasives is an agonizingly slow process, demanding flawless technique to avoid shattering the precious stone. A single pendant might represent not weeks, but years of a master carver's exclusive attention, supported by apprentices who prepared tools and maintained abrasives. In an economy without mass production, its value was astronomical, equivalent to perhaps 100 bushels of grain or a herd of livestock. Such an object was never merely jewelry, it was a portable treasury, a physical symbol of elite status because only elite patronage could command the years of a master's labor without requiring immediate practical output. This perspective illuminates the entire economic network. The flow of finely painted pottery, woven textiles, and bronze weapons across continents was not just an exchange of beautiful things. It was a complex balancing of labor equities. A bronze ingot traveling north might be traded for amber from the Baltic, not because they looked similar, but because the weeks of mining, smelting, and smithing skill embedded in the bronze were seen as equal to the dangerous months of diving and gathering needed to collect the amber. The artisan team, therefore, stood at the very heart of this system. They were the primary producers who transformed raw, low-value materials into high-value goods through the application of their coordinated skill. Their work created the surplus that fueled trade, and the wealth generated by that trade, in turn, fed back into supporting the workshops, allowing for greater specialization and more ambitious projects. The Grand Temple or the Royal Tomb was not just a spiritual statement, it was the ancient world's ultimate economic stimulus project, concentrating vast amounts of skilled labor and redirecting the flow of resources through an entire society. By counting the hours in a carved relief or the meals consumed to forge a helmet, experimental archaeology does more than price the past. It shows us that every artifact in a museum case was once a powerful economic actor, a silent negotiator in a forgotten marketplace of time, sweat, and human ingenuity. Yet for all its power, this method has clear and important limits. The reconstructed workshop is a stage, but we can never fully know the minds of the actors who once performed there. This is the essential humility of experimental archaeology. A modern researcher, no matter how skilled, brings a lifetime of modern assumptions, education, and even physical conditioning into the ancient workspace. Their hands may learn the motions, but their subconscious is wired differently. They lack the spiritual framework, the cultural taboos, and the unspoken social pressures that shaped every decision an original artisan made. We can recreate the tool, but we cannot inhabit the worldview that considered it an extension of the self, or a gift from a deity. This gap means our reenactments are thoughtful proposals, not recovered truths. They show us what was possible, and often what was most efficient, but they cannot tell us with absolute certainty what was always done. Another profound challenge lies in the problem of equifinality, a concept meaning that multiple different paths can lead to the exact same endpoint. Two separate teams, using slightly different sequences of actions or tool preferences, could potentially produce artifacts that look identical to us thousands of years later. An experimental project might prove one workflow is feasible, but it cannot disprove that another, now forgotten method was also used. The archaeological record often preserves only the successful final product, not the countless discarded experiments and local variations that preceded it. Our modern trials risk presenting a neater, more linear story than the messy, adaptive reality of the past. There is also the intangible element of ingrained, instinctive knowledge. A master craftsperson's skill was not a checklist of steps, but a deep bodily wisdom earned through a lifetime of repetition, beginning in childhood. A modern researcher dedicating a few years to a craft gains tremendous insight, but they are essentially a brilliant adult novice. They miss the neural pathways forged over decades, the subtle calibrations of force and touch that become as automatic as breathing. This lifetime of embodiment is perhaps the one thing we can never truly replicate. Recognizing these limits does not weaken the method, it strengthens its integrity. It transforms the goal from seeking a single definitive answer to mapping a landscape of plausible probabilities. Each experiment adds a data point, a tested piece of the puzzle. When multiple independent teams, using the same constraints, arrive at similar workflows and encounter the same physical problems, the proposed model gains credibility. The field progresses through this accumulation of tested, peer-reviewed attempts, always remaining open to new evidence that could overturn a previous understanding. This intellectual humility is its greatest strength. It reminds us that we are not resurrecting the past, but engaging in a long, respectful conversation with it. We are using our hands to ask better questions, knowing that the whispers we hear in reply are filtered through our own modern senses. The value lies not in claiming to have found the way, but in rigorously exploring the many ways human ingenuity could have bridged the gap between a raw material and a lasting legacy. A single discipline can only ask the questions it already knows. To truly converse with the silent workshop, we need a chorus of voices. The most powerful revelations in experimental archaeology rarely come from a lone scholar in a lab. They emerge from the vibrant, sometimes chaotic, intersection of wildly different fields. This is the interdisciplinary fusion, where the reconstruction of an ancient workflow becomes a melting pot of expertise, each contributor bringing a unique piece of the puzzle. Picture a single project to recreate a Viking Age sword. The traditional archaeologist provides the blueprint, the exact dimensions and metallurgy of the original artifact from a museum drawer. But then the team expands. A professional blacksmith, their hands from a lifetime at the forge, steps in. They look at the sword not as an object, but as a sequence of decisions. They can feel, in a way no report can capture, the precise heat needed to work the iron, the correct hammer angle to draw out the blade, and the intuitive moment to quench the steel. Their practical knowledge turns abstract theories about manufacturing into tangible, actionable steps. Yet the blacksmith's craft is only one layer. A materials scientist enters the workshop with a portable spectrometer, analyzing the microscopic slag inclusions in the experimental iron. By comparing this data to the ancient sword's own metallic fingerprint, they can verify if the modern team's smelting process accurately replicated the ore source and furnace conditions of 1,000 years ago. This hard data either validates the hands-on work, or sends the blacksmith back to adjust their technique. Meanwhile, an ethnographer might share studies of traditional blade makers in surviving cultures, revealing social structures around the forge, the ritualized aspects of the craft, and the nuanced ways knowledge is passed from master to apprentice without a single written word. This cultural context helps the team understand not just how the sword was made, but why certain steps were performed in a specific, seemingly illogical order. The convergence grows richer still. Sports physiologists might be invited to study the ergonomics of the work. They instrument the modern craftsperson with sensors, measuring the caloric burn, muscle strain, and optimal rest cycles involved in hours of hammering. This data helps model the physical realities of the ancient workforce, estimating how many people were needed to maintain production and what their nutritional requirements would have been. Even a historian specializing in obscure texts can change the entire experience. They might uncover a forgotten medieval manuscript that mentions a workshop foreman using a specific type of willow charcoal for fine detailing because it burned cleaner. This tiny textual clue gives the modern team a new variable to test, potentially solving a lingering mystery about the flawless finish on certain artifacts. This fusion does more than just add details. It builds a robust, holistic model. The craftsman's intuition is checked by the scientist's data. The historian's text is brought to life by the artisan's hands. The ethnographer's observations provide the social glue that holds the technical process together. Each expert acts as a check on the other's assumptions, preventing the project from veering into speculative fiction. The final recreated workflow is therefore stronger, more nuanced, and more credible because it has been pressure tested from every conceivable angle. It stands not on the authority of one field, but on the collaborative foundation of many. This interdisciplinary approach acknowledges a profound truth about the past. Ancient people did not live in segmented academic departments. They were at once engineers, artists, chemists, and storytellers. To understand their world, we must be willing to blend our own categories, to listen to the metallurgist and the poet, and to see the ancient workshop through a compound lens of shared human curiosity. The final step in any reconstruction is not taken in the workshop, but in the heart. To hold a replicated artifact is to hold a profound responsibility, a weight far heavier than the object itself. This is the essential, guiding principle of ethical replication, the moral compass that ensures our curiosity honors rather than harms the legacy we seek to understand. Experimental archaeology operates within a vital framework, one that recognizes that some knowledge is not merely technical, but sacred, and some processes are not just workflows, but living traditions. The field's highest purpose is not to perform ancient techniques, but to engage in a respectful dialogue with the cultures that created them. This begins with a simple, powerful rule: collaboration over assumption. Wherever possible, researchers now seek direct partnership with descendant communities, the living bearers of cultural heritage. This might involve inviting a master carver from a Pacific Island community to guide a project on traditional canoe construction, or consulting with indigenous elders about the appropriate use of certain pigments or symbols before attempting a replication. The goal is to move from speaking about a culture to listening to it, ensuring the work aligns with community values and contributes to their own goals of cultural revitalization and education. This collaborative spirit fundamentally shifts the work from extraction to exchange. It acknowledges that the deepest insights often come not from a microscope, but from a conversation. There are also clear ethical boundaries. Most practitioners agree that uniquely sacred or ceremonial items, those central to a community's spiritual identity, should not be replicated for public experiment or spectacle. The focus remains on the broader technical and social processes, the how of daily life and large-scale collaboration, rather than on appropriating the most intimate expressions of faith. A team might study the adhesive chemistry used in a ritual mask without ever attempting to recreate the mask's sacred form itself. This distinction preserves dignity and prevents the trivialization of deeply held beliefs. The ultimate aim of this ethical framework is to foster understanding, not to create a museum piece. When done with care, experimental archaeology can be a powerful tool for reconnection. For communities whose tangible heritage was lost or disrupted, seeing their ancestors' techniques successfully revived can be a source of immense pride and a catalyst for renewing craft practices. It transforms anonymous figures from the past into recognized innovators, their skill validated through modern scientific inquiry. This work becomes a bridge, built with respect and careful listening, that connects academic curiosity with cultural continuity. It reminds us that the ancient artisan team we have been following throughout this journey was more than a production unit. They were the custodians of a worldview, weaving meaning into every fiber and strike. Our modern exploration, therefore, must tread softly, guided by the principle that to truly honor their ingenuity, we must first honor the living culture that carries their legacy forward. The clay is still wet on the experimental potter's wheel, but the workshop is already being rebuilt in a new dimension. The tangible world of reconstructed tools and aching muscles is now merging with a virtual frontier, where the past can be simulated, stretched, and explored in ways once thought impossible. This is the next evolution, where experimental archaeology builds digital twins. Imagine creating a perfect, three-dimensional scan of an entire reconstructed Roman tile factory, from the clay pit to the firing kiln. This is not just a static model, it is a living system programmed with the physical properties of every material, the known techniques, and the estimated strength of a human worker. Within this virtual sandbox, researchers can ask questions that would take years to test physically. What happens to daily output if we add 2 more apprentices to the molding station, but only 1 more person to tend the kiln? The simulation can run this scenario 1,000 times in an afternoon, revealing bottlenecks in the workflow that might have taken an ancient foreman seasons to identify through trial and error. They can tweak the layout of a flint knapping site, moving the pile or the seating positions, and instantly see the impact on efficiency and safety. This digital layer allows for the exploration of infinite variables, testing not just how things were done, but how they could have been optimized, and what the hard limits of a particular system truly were. It becomes a laboratory for ancient logistics. The most profound potential, however, lies in collaborative virtual reality. Soon, a scholar in London, a master blacksmith in Norway, and an anthropologist in Japan could all put on a headset and find themselves standing together in a shared, immersive reconstruction of a Bronze Age foundry. They can pick up virtual tools that have the correct weight and resistance, feel the simulated heat of the furnace, and attempt to coordinate a complex pour as a team, despite being on opposite sides of the planet. This shared presence allows them to test theories of verbal communication in real time. Can they successfully direct each other using only gestures plausible for the era? Does a specific spatial arrangement of workers around a casting pit make the dangerous process smoother? These virtual collaborations will generate insights into group dynamics that are incredibly difficult to capture in a physical experiment. This digital frontier does not seek to replace the irreplaceable feel of flint in hand or the smell of a pine tar fire. Instead, it augments it. The physical experiment provides the ground truth, the authentic data on material behavior and human stamina. The digital twin then takes that validated data and expands it, allowing us to ask bigger, more complex questions about the systems that connected those individual efforts. Together, they form a powerful feedback loop, each refining the other, pushing our understanding of ancient collaboration into realms we are only beginning to imagine. The silent workshop is finding a new voice, not in the echo of a hammer, but in the silent, boundless space of the virtual world, where every variable is a question waiting to be asked. The silent workshop finds its most powerful voice when it steps into the light of day, shared with the living. This is where experimental archaeology transcends academic journals and becomes a public spectacle of rediscovery. Living history museums and heritage sites are the modern stages for these ancient workflows, transforming passive observation into an immersive encounter. You are no longer looking at a static display case. You are standing at the edge of a reconstructed Roman forge, feeling the wave of heat from the furnace, smelling the charcoal smoke, and hearing the sharp ring of hammer on bronze as a team of interpreters, their hands stained with patina, coaxes a molten pour from a clay mold. The process is no longer a theory in a textbook. It is a tangible sensory reality unfolding in real time, with all its inherent risks and triumphs. This public performance does something profound. It demystifies the monumental. Watching a team of 4 people, using nothing but ropes, wooden levers, and their own coordinated strength, slowly raise a massive timber frame into place for a Viking longhouse, makes the scale of ancient construction suddenly comprehensible. You witness the communication, the shared strain, the moment of collective triumph as the post slots home. The abstract idea of building a cathedral collapses into the relatable human effort of a team solving a heavy problem together, right before your eyes. Documentary filmmakers have become essential partners in this public translation, using slow-motion cinematography and intimate storytelling to highlight the nuance within the action. A close-up on a potter's hands, the subtle tremor as they pull a perfect clay wall from the spinning wheel, speaks volumes about the skill involved. A narrated sequence following the year-long journey of a single oak tree, from forest to finished Longship plank, instills a deep appreciation for the material intelligence and patience embedded in every artifact. These public demonstrations and films create an emotional bridge. They allow a child to look at a bronze spearhead in a museum and not just see a weapon, but remember the sweat on the brow of the person who cast it. They allow an adult to understand a woven textile as a calendar of human labor, each thread representing hours of careful work. This engagement turns the ancient artisan team from an anonymous historical concept into a group of recognizable, skilled individuals, people we can admire and even empathize with. Their challenges become our shared human challenges, their solutions a testament to universal ingenuity. By bringing the workshop to life for all to see, this discipline ensures the legacy of these teams is not locked in the past, but continues to resonate, educate, and inspire a sense of connection to the countless hands that literally shaped our world. The reconstructed workshop falls silent, but its story now echoes far beyond its walls. Our journey from the quiet earth of the quarry to the roaring heat of the forge has traced more than a technical process. It has mapped a profound human truth. Experimental archaeology does far more than solve historical puzzles. It breathes life back into them. By painstakingly recreating the workflows of ancient artisan teams, we do not just learn how a granite vessel was drilled or a longship was riveted. We begin to hear the subtle, unspoken language of their collaboration, the rhythm of coordinated effort that turned individual skill into a collective force. We gain a tangible appreciation for the staggering scale of their endeavor, measured not in abstract years, but in the ache of muscles, the patience of countless days, and the shared focus of generations. This method allows us to marvel at the distributed intelligence that raised monuments and built empires, an intelligence woven into the very fabric of social cooperation. These experiments serve as a powerful reminder that behind every timeless artifact resting in a museum case, behind every silent stone of a pyramid or every stitch in a faded tapestry, lies a vibrant human story. It is a story of people solving problems together, trusting one another's expertise, and passing hard-won knowledge from hand to hand and heart to heart. The true legacy uncovered here is not merely the object itself, but the enduring testament to our species' timeless capacity for collective creation. Our curiosity about the past is, at its core, a quest to understand the fundamental ways we have always worked together to shape our world. If this exploration into the heart of ancient teamwork has given you a new lens for viewing history, we would love to hear your thoughts in the comments below. Consider subscribing to join us as we continue to resurrect the lost chapters of human ingenuity, one reconstructed collaboration at a time.